Strength in acidity of hydrated cations is where we got to the last time. And I explained these concepts. How do we determine which hydrated cation is more acidic than the other? There are two ways of determining it. If you have the elements are different, the cations are different, and they have the same moles of water, say X. Charge density is what is key. The higher the charge density, the stronger the acid, or the stronger the strength, or the higher the strength of that acid, that hydrated cation acting as an acid. The higher the charge or the greater the charge density, the more acidic the hydrated cation is. How does it happen? Well, charge density is high, it attracts a lot of water molecules, it withdraws electrons in the OH bond. That bond becomes weaker, so hydrogen plus is released with ease, making the acid a stronger acid. Then you know the factors that affect or that determine charge density is the charge over size. Charge over size is charge density. So you can determine. That is if the cations are the same, or they are in the same, they have the same charge. Let me put it out. They have the same charge. Then size is what helps you determine that. The other alternative is if the cations are the same, they are the same cation, same magnesium, so they have the same charge. You can't use charge density because all of them will have the same charge density. They have the same size and the same charge because they are atoms of the same element. In situations like that, the number of molecules of water around the cations will be different. They will certainly be different. So you look out for the one that has the higher number of molecules of water around the cation. That one is a stronger acid because the more water molecules you have around the central atom, what it means is that the more H plus you have available to release the solution, the more acidic you are. So that actually brought us to the end of the BrØnsted-Lowry concept. Let's quickly look at the last concept. I think we spent too much time on these definitions, these people's definition of acids and bases. But it's important to understand these things, especially when you made me understand that Mr. Mansu focuses more on calculation than theory. So you need to understand what the theory is. Anybody knows why Dorcas is no longer coming to the class? I don't remember the last time I saw her in the class. Okay. Anybody has any answer for me on that? Why Dorcas is no longer coming to the class?
Yes, sir. She said the network problem.
You spoke with her?
Yes.
Okay. All right. Thank you. Gilbert Newton Lewis is the next person is the last person we want to look at. He propounded his theory, or he introduced his theory, his definition of acids and bases in the year 1923. In the year 1923, the name is G.N. Lewis. But in present day chemistry, you always see Lewis. He is known for a number of things in chemistry. One of the things he's known for is what we call electron dot structures, which we call Lewis electron dot structures under chemical bonding. Okay, if we do chemical bonding, you get to know what we call the Lewis electron dot structures. So just know the name and know when the theory was introduced. The definition of acid and base was introduced in 1923. And the Lewis definition is the most general theory, having no requirement for solubility of protons. His theory is more general. As for his theory, anything at all can be an acid. Well, not anything at all. Once you can donate electrons, or if you are positively charged, you can be an acid. If you are negatively charged, you can be a base. So what did he say? According to Lewis, an acid is a substance that can accept a pair of electrons to form coordinate covalent bond. I have a question for you, and Jasper will answer this question, because I remember I had a class with you some time ago in the past where we look at bonding or so, and then we look at covalent bond, we look at coordinate covalent bond. So my question to you, Kuma, Jasper, Papali, is that what is first covalent bond, and second coordinate covalent bond, and third, what is the other name for coordinate covalent bond? The first one. Okay, it doesn't look like Jasper can hear me. Article Iris. Okay, Article Iris 2 cannot hear me all of a sudden.
Yes, sir.
Oh, thank God, she can hear me. What is covalent bond? Bisa, Nana Kofi, what is covalent bond? Okay, in JHS, well, not even here in secondary school, I'm sure Mr. Mansu taught you. One of the types of bonds, interatomic bonds. Okay, Tenuka, any idea what covalent bond is?
Sir, covalent bond is formed as a result of the sharing of electrons between two atoms or more.
Yeah, between two atoms. Between two atoms at a time, between two atoms. That's good. So that's covalent bond. Okay, there's a type of bond we call ionic bonding. Ionic bonding. That's the first interatomic bond you were taught in under bonding or in bonding, where one element donates the electron, another accepts. Then a force of attraction, an electrostatic force of attraction, holds them together. That force is all called a bonding, the ionic bond. So ionic bond is defined as the electrostatic force of attraction between a positively charged species and a negatively charged species. That's ionic bond. So one donates, another accepts. Now, there's another type of bonding where the atoms, none of them donates, another accepts. Rather, both of them donates and they share the electrons that are donated between them. If you look at the diagram for like a two-set problem, the electrons, stay in that intersection over there. It belongs to both of them. I remember in JHS, when our teacher was teaching us covalent bonding, the one term he used a lot, used to describe this is NC, no contribution, no chop. contribution, no chop. That's what happens in covalent bonding. You bring 2 electrons, I also bring 2 electrons, then we share it, then it belongs to the 2 of us. So we have 4 electrons that belongs to each one of us. So covalent bonding, like Carriage rightly said, is a type of bond that involves the sharing of electrons between 2 atoms, or which is formed as a result of the sharing of electrons between 2 atoms. Coordinate covalent bond is a type of covalent bond. But in this type of covalent bond, the electrons that are shared between the 2 atoms, whether it is 2 electrons, 4 electrons, all of them are donated by only 1 atom. So only 1 atom donates the electron, then it is shared between the 2 atoms. That's coordinate covalent bond. So anytime an atom donates an electron, another just accepts, then they form a type of bonding we call coordinate covalent bond. One of the conditions necessary, or there are 2 conditions necessary for the formation of coordinate covalent bond. One of them is that one of the atoms must have empty orbitals to accept electrons. Then the other atom must have lone pairs of electrons on it to be able to donate, because you need to be able to donate the electron. Lewis is saying that any substance that has empty orbitals capable of accepting pair of electrons to form coordinate covalent bond is an acid. Any substance that can accept a pair of electrons, and I want you to know the difference between what Lewis say and what BrØnsted-Lowry say. If not, you confuse yourself. As for BrØnsted-Lowry, an acid is a donor. And what are they donating? Proton, not electron. An acid is a proton donor. That's BrØnsted-Lowry. An acid is a proton donor. That's BrØnsted-Lowry. Donor. In Lewis, an acid is an acceptor. Acceptor of what? Not protons, but of a pair of electrons. A base, according to Lewis, is a substance that can donate a pair of electrons to form coordinate covalent bond. It's the direct opposite of the acid. And again, BrØnsted-Lowry's base is an acceptor. BrØnsted-Lowry, he says a base is a proton acceptor. That's what he said. Proton acceptor. Not electron acceptor, but proton acceptor. But Lewis is saying that a base is rather a donor, not a proton donor, but a pair of electron donor to form coordinate covalent bond. Lewis acids and bases react to create an adduct, a compound in which the acid and then the base have bonded by sharing the electron pair. Sure, when they come together, the compound they form is sometimes referred to as an adduct, because you have one species donating electron, another species accepting the electron. Then the 2 atoms, clinch together and stay as one entity. Lewis acids and bases or acid-base reactions are different from redox reactions because there's no change in oxidation states. Lewis acid-base reactions are not redox reactions. Okay, I'm sure you know what redox reactions are. Redox reactions are those reactions in which there is change in oxidation number of relevant species. Okay, all right. Lewis acid-base reactions are not redox reactions because no species oxidation number changes, increases or decreases. No. Now let's look at examples of Lewis acids. Then we'll look at examples of bases. All cations, especially transition metal cations, all of them, cations. Once they have a charge, you are an acid, according to Lewis. Why? Because the charge means that you have lost electron. And so you have empty orbitals to accept electron from anybody who wants to donate to you. All cations, singly charged cations, are Lewis acids, but most especially the transition metal cations are Lewis acids. See, so the examples I've given you, H plus, copper 2 plus, iron 3 plus, aluminum 3 plus, manganese 2 plus, zinc 2 plus, vanadium 5 plus, iron 2 plus, and so on and so forth. All of them, they are Lewis acids. Because I said the plus means that they have lost some amount of electrons, and so there is vacuum or there is space, empty, for anybody to donate electrons into them. Kuma Jasper, can you hear me now? Oh, wow.
Yes, sir.
Okay, that's fine. Then 2, neutral molecules whose central atoms have empty atomic orbitals to accept electron pair are also examples of Lewis acids, neutral molecules. You see examples I've given here. Aluminum chloride, boron chloride, and so on and so forth. They also act, they are neutral molecules, they have no charge. They also act as Lewis acids because they are central atoms. Very often the elements that are written first are the central atoms. Then the most electronegative elements, become what we call surrounding atoms because they surround the central atom. Now, if you write the electronic configuration of all those atoms I have given, or the central atom for all these compounds, you see that they have empty orbitals. Let's try. Take a look. Okay, let's do the second one. It's even easy to do the second one. Boron. The electronic configuration is 1s2, 2s2, 2px1. Atomic number is 5. Okay, so 2px1. Once one electron has entered into the second shell, it means you have 2py there, 2pz there. They are there. They are on that shell. But they're empty. They're empty. So they can accept electrons from anybody who wants to donate it. Okay, in fact, I don't know whether you did what we call hybridization. Hybridization happens prior to covalent bonding. The electronic configuration of boron that I have just mentioned for you, that's what we call the ground state electronic configuration. Ground state. At the excited state, one electron leaves the 2s orbital. So you have 2s1 and 2px1, and then one electron goes into the 2py1. That's the excited state electronic configuration. So boron is able to miss the 2s orbital, misses the 2px, and then the 2py orbital. The three of them mix together. It gives what we call xp2 hybridization, because you are mixing one s orbital, which is actually the 2s orbital, and then you are mixing two p orbitals, the px and then the py. So it forms 3 new what we call hybrid orbitals of the same energy level and of the same shape. Each one of them is called sp2. 3 of them are formed, xp2, 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 3 of them. Okay, then the 3 atoms of chlorine, and each one of them has just 1 electron in it. Each one of them will have just 1 electron in it. So the 3 atoms of chlorine bond with each one of them with 1 electron. But you realize that in the boron, you have a 2pz orbital left. You have a 2pz orbital without any electron. So you have empty orbitals to accept. It has empty orbitals to accept electrons from whoever is willing to donate. And because he has empty orbitals to accept electrons, it then acts as a Lewis acid. The same thing applies to aluminum. Write the configuration of aluminum. You have 1s2, 2s2, 2p6. That's 10. Okay, aluminum is 13. You have 3x2, and then you have 3px1. So you have 3pxy, 3py, and then 3pz. empty. You have 3py and 3pz empty. So you can accept lone pairs of electrons into orbitals because it has empty orbitals to accept electrons. It makes it behave as a Lewis acid. By the way, what are lone pairs of electrons? What is a lone pair of electrons? Or what are lone pairs of electrons? Bisanana copy. Can you hear me now? Daniel, how are you?
Sir,
Yes, Abisa.
sir, please, yes. Now I can hear you.
Did you hear my question? What are lone pairs of electrons?
Okay. Low
This if you can hear me, your connection is so bad. Your network is so bad. The voice is breaking. We can't hear anything. I think you need to work on that, okay? Daniel, how are you? What are
electrons that do not take part in bonding?
okay? I think I heard you quite clearly. But Daniel, how are you? What do you think? What are lone pairs of electrons?
So, lone pairs of electrons are the valence electrons that are not shared with any other atom in covalent bonding.
Yeah. There are those pairs of electrons that remain on the valence shell of the atom. They are not involved in bonding. They are not used in bonding. They are called lone pairs of electrons. They are not involved in bonding. To identify Lewis acids, look for species, ions, atoms, etc., that have valence shells that can accept electron pairs. That's how you identify Lewis acids. And the two examples, I've given you a broad example of example. In fact, all cations, you know, if you're a cation, you can be a Lewis acid because the plus on you means that you have lost electrons. So orbitals are empty. Examples of Lewis bases. All single atoms with negative charge. All single atoms with negative charge. Simple anions. F minus, Cl minus, S2 minus, O2 minus, etc. Once you have a negative charge, what does it mean? It means you are electron dense. You have electrons. You have excess electrons that you can donate to any atom. So you have pairs of electrons that you can donate. It makes you a Lewis base because that's what a base is according to Lewis. A base is an electron pair donor. And you can only donate when you have. You cannot donate what you do not have. So they have electrons, plenty. The minus sign means they have accepted other people's electrons. So it's with them. So it makes them rich in electrons that they can donate to anybody who needs it. Can you see the kind of things Lewis says are bases and are acids? These things are not bases and acids in the regular, lab that we when we're talking of acids and bases. We don't talk of these charges. They are not acids nor bases, but that's his definition. Okay, and that's one of the flaws or the major flaw, weakness in his definition. Once you can be positively charged, you can be an acid. Once you can be negatively charged, you can be an acid. You can be a base, and that's dangerous. The second one, neutral molecules whose central atoms have lone pairs of electrons to donate. If you have a lone pair of electrons to donate, you are a Lewis base. And these molecules, H2O, water, SO2, SO3, ammonia, then these are alcohol, these are amines, compound, organic compound, amines. The R there means an alkyl group, CH3, CH2, CH3, CH2, CH2, and so on and so forth. Okay, OH is a functional group we call alcohol or alkanol. Then NH2 also denotes a functional group we call amine, and so on and so forth. Now, if you did the hybridization and you once attempted drawing the structure of water, the structure of water looks like this. If you draw what we call the Lewis electron dot structure, you have the oxygen there, then you have the two hydrogens. You have the two hydrogens around the oxygen like this. And then if you draw the structure well, you see that there will be, you have two lone pairs of electrons on the oxygen. You have one here, this is a pair of electrons. You know, a pair is made up of two things. Then you have another one also at this side. You have another one here. Yeah, it's just two pairs on the oxygen in water. If you draw the Lewis structure, a structure like this is what we call the Lewis electron dot structure, where dots are used to represent electrons. We call it Lewis electron dot structures. The kind of hybridization that happens in water is XP3 hybridization. And water has a shape we call a bent shape or a V shape because the two electrons there, the two lone pairs, repel each other. They repel each other, that they repel the bonds. What is in the bonds are also electrons. So they repel the bonds, the electrons to the bond, so that it curves, it goes inside as if V, as if the letter V. So we say water has a V shape or a bent shape, is bent, okay? But the lone pairs on oxygen in water means that water has electrons to donate. It can donate to any atom whose orbital is empty. So it makes water a Lewis base. For all the compounds I've written here, if you draw their structures, you have a lone pair on the central atom. Ammonia is like this. Ammonia is this N, then it shares one electron, or it shares two electrons with hydrogen to the right, shares another one up, because the hydrogens are three, shares another one down, okay? And then there is a lone pair. There is a lone pair on the nitrogen. If you draw the Lewis structure very well, I'm not drawing Lewis, I'm not showing how to draw Lewis structures, maybe some other time. When you come back to school, we have the time. There's a lone pair on the nitrogen. Okay. The ammonia also has what we call XP3 hybridization, because there are 4 electron groups around the nitrogen. XP3 hybridization with a specific shape. It belongs to a general shape we call tetrahedra. The shape is generally referred to as tetrahedra, but because tetra means 4, but because one of the 4 electron groups is a lone pair, specifically has a shape we call trigona pyramida. Trigona pyramida, and so on and so forth. But the lone pair on nitrogen, this lone pair means that it can donate the lone pair into any orbital that is empty. And because of that, it makes ammonia act as a Lewis base. Okay, the molecules with pi bonds, like oh, this should be 18, not 18, like CH2, CH2. Let me change it at once. That molecule should be it should be 18. That should be E, not A. 18. CH2, CH2. Where there are pi bonds are formed normally when you have multiple bonds, double bond or triple bond, then you have a pi bond form. When you have a single bond, it's just a bond we call sigma bond, sigma bond. When you have two bonds, one of them is sigma, the other is pi. Pi bonds are weaker than sigma bonds. Sigma bonds are stronger. They are formed by what we call head-on overlap of orbitals, atomic orbitals. Atomic orbitals. These things happen after hybridization. Okay. Then, so those bonds are stronger than pi bonds. Pi bonds happen, they are formed by side-by-side overlap. You know, orbitals, like normally the p orbital. See, the p orbitals has a dumbbell shape. It looks like the figure 8. So they come side by side. Okay, then they form what we call the pi bonds. Those bonds are weaker. If you have a triple bond, like what is this in nitrogen gas? 2 atoms of nitrogen are connected by a triple bond. If you have a triple bond, one of them is a sigma bond, 2 of them are pi bonds. So molecules with pi bonds, molecules that have multiple bonds, either double bond or triple bond, also act as Lewis bases because they have lone pairs of electrons to donate. To identify Lewis bases, look for species that have lone pair electrons that can be donated to form a covalent bond. I explained that already. Now, these are classical examples of Lewis acid-base reactions. The first one, what you see over here is nothing, it's not anything so complex. This is ammonia, this one, that's ammonia, it's NH3, okay? I drew the structure before. Ammonia, if you draw the Lewis electron dot structure for ammonia, it has a lone pair on the nitrogen. So here, what you see here is nothing so special. It's just nitrogen sharing electrons with each of the 3 atoms of hydrogen. So it shares one to the left, one to the right, one bottom, okay? Then in the next equation, you see I've used a dash. When 2 electrons are shared, in other words, when one pair of electrons is shared, it's equivalent to just a dash. When it shares 4 electrons, that's 2 pairs of electrons, then you have 2 dashes and so on and so forth. So that's just ammonia. That's the Lewis electron dot structure for ammonia. Plus a proton, H plus. You see, H plus. The H plus means that he has lost electrons. So he has lost 1 electron. He has empty orbital to accept. So ammonia donates this lone pair into the empty orbital of hydrogen or proton. Then it forms what we call ammonium. That's how ammonium ion is formed. The NH4 plus. Here is it. See, nitrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen. It comes with a charge. Okay, it comes like this. Then you see a positive charge at the top here. And the type of bonding involved in this process, we call it coordinate covalent bond. Coordinate covalent bond. Ammonia, the nitrogen on ammonia donates these 2 electrons. Look at it. And you see it being shared here. The 2 electrons are being shared here, where I'm circling. Let me use a different color. The 2 electrons are being shared here between the nitrogen and then the hydrogen to the top of it. Which is this hydrogen, this one. Yet the 2 electrons are donated by only 1 atom or only 1 molecule, ammonia, that is shared between the 2 of them. We call this type of bonding coordinate covalent bond. Now, look at this one. The one to the the one to the right, this one. You have H plus. That's a proton. Then you have OH minus, hydroxide. Because it is minus, what it means is that it has lone pairs of electrons to donate. And you can see the lone pairs of electrons, 3 of them. So it donates, some of these lone pairs of electrons into, in fact, it donates one, not some, because hydrogen can only take 2 electrons. It donates only 1 pair into the empty orbital of hydrogen. Or it donates 1 and it shares it with hydrogen. Then you see the 1 hydrogen come. And then you'll be left with 2 lone pairs of electrons on the oxygen. And this is water. This is actually how an equation depicting the formation of water. The bonding there is coordinate covalent bond. So the OH minus is the base, is the Lewis base because it's the one donating the electron pair. And then the H plus is a Lewis acid because it's the one accepting the electron pair. Another example is what you have, the reaction between ammonia and boron trifluoride. Okay, boron trifluoride, if you observe, is one of the examples of acids that I gave you at the previous page. BF3. It has empty orbitals. There are empty orbitals in boron, so it accepts the lone pairs of electrons from ammonia, the nitrogen of ammonia. Then it forms this compound, forms this whole compound. These are all organic compounds. We can actually give the name, the IUPAC name for these compounds. Then there are others that are just, like this. Copper normal, in fact, the formation of complex ions, okay, happens through this process. Complex ions where you have the central atom being a transition metal surrounded by certain molecules of, another element, mostly inorganic. They are what we call complex ions, And most of them are formed of complex species. Most of them are formed through this coordinate covalent bond. In the case of this, again, you see ammonia. Ammonia has lone pairs. Ammonia always has lone pairs. You donate it into the empty orbital of copper. Then it gives you this complex. Cu NH3 subscript 4 plus 2 because the charge of copper is plus 2. Any question? These are Lewis acid-base reactions. Anybody has any question for me? Okay. I am going on. Look at this question. Account for the following observation. BCl3 and PCl3 are both covalent compounds. BCl3 and PCl3 are both covalent compounds. BCl3 acts as a Lewis acid, whilst PCl3 acts as a Lewis base. Why? If you look at the compounds, they have the same number of chlorine atoms. They look similar, their structure in terms of structure. But why is this? Why is the boron chloride acting as a Lewis acid, whereas the phosphorus chloride acting as a Lewis base? It's about writing the electronic configuration for the central atoms. The central atoms. Now, when they say one thing acts as a Lewis acid, explain why. You can only act as a Lewis acid if you have empty orbitals to accept electrons. So you need to know that. You need to find out whether there are empty orbitals. And normally, the reference is with the central atom. If you are to explain why one species acts as a Lewis base, you can only be a Lewis base when you have lone pairs of electrons to donate. And mostly it's with the central atom. And I said the central atom is most often, most of the time, the atom that is the most electropositive element. All right. Now look at the explanation. In BCl3, the one that is acting as the acido, the electronic configuration of boron is 1s2, 2s2, 2px1. Excited state is, okay, I think I explained this. If you write the excited state electronic configuration, you have 1s2, 2s1, 2px1, 2py1. I explained that this electron, one of these 2s2 electrons, this one, will go into the 2py. That's at the excited state when it absorbs a lot of energy. So that you have only one electron there, and then one of the electrons it has donated is gone into the 2py. So boron mixes the 2s, 2px, and then the 2py orbitals to form 3sp2 hybrid orbitals. I explained that too. Now it uses these 3 orbitals to overlap head-on with 3 atomic orbitals of 3 chlorine atoms to form 3 sigma covalent bonds. But there is one orbital left. Boron, after bonding, has an empty 2p orbital, that is a 2pz. I explained that to accept lone pair of electrons. Boron chloride therefore behaves as a Lewis acid. It's just because after the excited state, only these orbitals are mixed, the 2x, the 2px, and the 2py. The 2pz orbital is left empty. And because it is empty, it makes boron chloride behaves as a Lewis acid, because Lewis acids are electron pair acceptors. You can only accept electrons if you have empty orbital. That's the reason why boron chloride behaves as a Lewis acid. Now you can imagine the opposite will be for the phosphorus chloride, because that one have lone pairs to donate. Look at it. Now in phosphorus chloride, phosphorus shows xp3 hybridization. That is, so you write the electronic configuration for phosphorus. You have x 1s2, 2s2, 2px2, 2py2, 2pz2, 3s2, 3px1, 3py1, 3pz1. Phosphorus atomic number is 15. All the p orbit, the 3p orbitals will be halfly filled. Now, what happens is that phosphorus mixes the 3x, you see the 3x, 3px, 3py, and 3pz. It mixes all those orbitals to form 4 xp3 hybrid orbitals. It forms 4 different orbitals. We call xp3. 4 of them, xp3, 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 4 of them. They are of the same energy. They are new orbitals. In fact, we define hybridization as the mixing together of different atomic orbitals of different shape and of different energy level. They're of different shape. You know, the s orbital is spherical. Yeah, the s orbital is spherical in shape, but the p orbitals are dumbbell shape or dumbbell shape. They look at the figure 8. So hybridization is the mixing together of orbitals, atomic orbitals of different energy and shape. Those orbitals I've mentioned, the x and then the p, they are of different shape. One, they are of different energy, but you mix them together, then you form orbitals. You form new hybrid orbitals of the same energy. The ones you form will then become of the same energy. We call that process hybridization. So in phosphorus, when that happens, you have 4 new hybrid orbitals, each one of them called xp3. xp3 because you miss 1 s, and then you miss 3 p orbitals. You miss all the 3 p's, the px, the py, and then the pz. But you realize that, so you have 4 orbitals available. But you realize that when it's combining with chlorine, you have just 3 atoms of chlorine. So it will use 3. So The phosphorus uses 3 of these orbitals, each containing unpaired electrons. Each one of them comes with 1 electron each, to overlap head-on with 3 chlorine atoms to form 3 sigma covalent bonds. Phosphorus, after bonding, has a lone pair of electrons, which can donate to form a dative bond. So it uses 3 to bond with each, to form a sigma bond with each of the 3 atoms of chlorine that surround it. Then there will be 1 left. There will be 1 sp3 hybrid orbitals there, because it's 4. 4 of them are formed. 1 will be left with 1 electron in it there. Okay. That makes it behave as a Lewis base, because it has electron pair to donate. It has excess electron pair to donate to anybody who needs it. That is the reason. That is the reason why boron trichloride or boron chloride and phosphorus trichloride, even though they look alike, one of them, BCl3, acts as an acid, whereas the other, PCl3, acts as a base. Any question? Any question on that explanation? It's very important. Any question, any species you are asked to explain why this acts as a Lewis acid, or find out whether it has empty orbitals. If it has empty orbitals, that's it. That's the reason. That can only be the reason why a species can act as a Lewis acid. That can only be the reason. And sometimes it's the electronic configuration you use. Other times, when you need the electronic configuration, you can deduce. If I give you H plus and I ask you, explain why H plus is a Lewis acid. The hydrogen has 1 electron. The plus over there means it has even lost that 1 electron. So it has empty orbital. If you have an empty orbital to accept an electron, you are an acid now, according to Lewis. Then I give you a species, explain why this species is a Lewis base. Just write the electronic configuration. You will see what it is pairing with after bonding, after hybridization and bonding. 1 electron will be left, or a pair of electrons will be left in some orbitals that are not used in the bonding. It means it has electrons in excess to donate to anybody who needs it. Well, because you have excess electrons to donate, you obviously act as a Lewis base, because a Lewis base is an electron pair donor. Any question on that explanation? Is very important you understand that concept. Absolutely important. Am I talking to people who are alive?
Yes.
Theophilus.
Yes, sir.
Theophilus, leave your mic on. Do you understand?
Yes, sir.
I'm a mature courage. Do you understand my explanation? Dogbe, Rosalind, said the name. Hey, you also there?
Sir, please, I just came
You just joined the class.
like 10 minutes ago.
Why?
So there is network problem.
Where are you not in Ho?
No, I
Where?
went to my grandma's place
At where?
at Pengwe. Pengwe.
Oh, okay. I hear you.
After Barrack Newtown.
After Barras Newtown. Okay, I hear. That's fine. It's okay. All right. So let's bring this concept to an end by looking at similarities and differences between these people's definitions. And this invariably is the same as their strengths and their weaknesses. That's what you have on your slides now, on your screens now. So between Arrhenius and BrØnsted-Lowry, look at what I put there. Arrhenius and Arrhenius, I say acids and bases are determinately in aqueous solution. You remember that theory? According to Arrhenius, you can only tell what is an acid or what is a base when there is water. And that's dangerous. So you see, that becomes a weakness of his theory. So if there is no water, I can't determine what an acid is. Is that what you are saying, young man? That becomes a weakness of his theory. BrØnsted-Lowry, on the other hand, but this, what I'm giving you are differences. So whilst alkenols require an aqueous medium to determine what an acid and a base is, BrØnsted-Lowry doesn't require any medium. Acids and bases are determined in any solvent, including gas phase. Okay, what I mean by that is it's not restricted to water. It's not restricted to aqueous medium. You can determine what the BrØnsted-Lowry acid is everywhere, whether there's water or not. Or even if there is gas, you can determine it. Even if there is solid, you can determine it. Even if there is nothing, you are in vacuum, you can determine it. Just just see what is donating a proton, that's all. That's a BrØnsted-Lowry acid. See what is receiving a proton. That's a base. So one of the flaws of Arrhenius theory is that you only determine what an acid is and what a base is when there is aqueous medium. So if there's no aqueous medium, you can't know whether a substance is an acid or a base. Now, between Arrhenius and Lewis, one difference is under Arrhenius, it occurs only in water. I said that earlier. But Lewis, it occurs in water, non-aqueous, solvent, or gas phases, just like BrØnsted-Lowry too. When I was giving you Lewis definitions, he didn't say in aqueous medium or in gaseous medium or in any medium. It just says a substance that is capable of accepting electron pair is an acid. That's Lewis. So whilst Arrhenius occurs in water, Lewis occurs anywhere, any of the phases. Could be water, liquid, it could be gas, it could be solid, any phase. You can determine what an acid is, you can determine what a base is. Now, another difference between Arrhenius and Lewis is that under Arrhenius, species must contain hydrogen and OH to be acids and bases respectively. Under Lewis, it is not limited to H and OH containing species. You saw that. I think one other difference you can write here, it just came to my mind, is that under Lewis, species must be charged. No. Well, yeah, I guess because you have neutral species too. That can be Lewis acids and bases. But that's another difference. For Arrhenius, if you don't contain hydrogen, you cannot be an acid. If you don't contain OH, you cannot be a base. And you see, this is another weakness of Arrhenius theory. One of the weaknesses is the fact that you need aqueous medium only to be able to determine what an acid and a base is. Another weakness is this difference. Because look, we have bases like ammonia, NH3. Ammonia is one of the best or one of the common bases we use in the lab. Yet it doesn't contain OH in it. When it dissolves in water, it produces ammonium hydroxide. But ammonia, as it is, doesn't have OH in it. So Arrhenius doesn't classify ammonia as a base. But can you imagine? You see, that's a weakness of his theory. The fact that you must contain OH, you must contain H necessarily before you are called an acid or a base is a huge flaw in his theory. Now, differences between BrØnsted-Lowry and Lewis. So first it was Arrhenius, BrØnsted-Lowry. Then second, Arrhenius, Lewis. And this is the last one, BrØnsted-Lowry, Lewis. Under BrØnsted-Lowry, species must contain H to be acids. Under Lewis, it is not limited to H and OH containing species. Oh yeah, that's it. You see the same thing under BrØnsted-Lowry. You must contain hydrogen to be an acid. Lewis, you don't need hydrogen to be an acid. Now, similarities between the two theories, BrØnsted-Lowry and then the Arrhenius. Acidic species contain hydrogen in both theories. You can imagine that. You can see that. In both Arrhenius theory and BrØnsted-Lowry theory, anything that is an acid contains hydrogen. So that's a similarity between them. You are not an acid if you don't contain hydrogen in any of these two theories. BrØnsted-Lowry acid, a proton donor. Proton is hydrogen. So if you don't contain the hydrogen, what are you donating in the first place to be called an acid? So it's a similarity, both of them. Arrhenius is an acid substance that contains hydrogen, and when dissolves in water, produces excess hydrozonium ion, or H plus, as the only positive ion. Again, the mention of hydrogen is there. So it becomes a similarity between the two theories. Maybe you should be guessing, no, not guessing, you should be, let's brainstorm. That's all that I have. Do you see any other similarities between Arrhenius and BrØnsted-Lowry? That's one. Or between Arrhenius and Lewis? That's two. Or between BrØnsted-Lowry and Lewis? Anything that is similar to both theories. Let's use 2 minutes. Think about it and tell me what you think. 2 minutes. Think. Any similarity or even any difference that you think I haven't listed in them. 2 minutes. Just think. Think about the three theories. All right. Any information? Anybody thinks about something or nobody is thinking? Is anybody thinking amongst you to have thought about something? Awaga, Cromwell, Cromwell, Jason, did you think about something? Tenu courage.
Yeah.
Anything comes to mind?
Not yet.
You people are not thinking proper.
So please, I want to give for Lewis and BrØnsted-Lowry. So for
can you give me a
Lewis,
difference or similarity
difference.
between Lewis and BrØnsted-Lowry?
Yeah.
All right.
So for Lewis, for it to be classified as one, need to have an empty orbital to accept a lone pair of electron or a lone pair to donate. But for BrØnsted-Lowry, it's not limited to that.
Yeah. 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 That's a good, thought. That's a very good thought. For BrØnsted-Lowry, we're not interested in whether you have a lone pair. So basically, you are using their definition as a difference, and that's good. You don't need to have a lone pair of electron to be called an acid or a base. You don't need to have empty orbital to be called an acid or a base. For Lewis, you need to have empty orbital to be called an acid, lone pair of electrons to be called a base. That's good. That's good. I accept that. So if you go to an examination and then they say, give two differences between BrØnsted-Lowry and Lewis theory, then you say the teacher gave you only one. That's all. Some people write the one and the second one they say, hey, Master, the teacher gave us only one. Why are you asking us for two? But that's something you can add. So that brings us to the end of those theories and all the things they've said about acids and bases. It's taking us more than a month to do this. But that's fine. The next thing I want to talk about, which I'll be very brief, quick, is what we call basicity of an acid. We've spoken about this before, where when we spoke about this, there we call it monoprotic. You remember monoprotic and polyprotic acids. Monoprotic acids are those acids that can ionize only one H plus. Polyprotic can ionize more than one. If you can ionize two, you are specifically called diprotic. If you can ionize two, three, triprotic, four, tetraprotic, and so on and so forth. It's the same theory here. But this one, the number of hydrogen ions that an acid can ionize is the basicity of an acid. An acid, but we're talking about base, and we have acidity of a base. So the basicity of an acid is defined as the number of ionizable H plus ions present in an acid or in the acid. If you can ionize one, if you have one, then we say you are monobasic acid. So when you hear questions like this, define a monobasic acid. Monobasic, then they say acid, monobasic acid, monobasic acid. What is a monobasic acid? What is a dibasic acid? What is a monobasic acid? What is a dibasic acid? So a monobasic acid is an acid that can ionize only one H plus ion. It's an acid though. Monobasic acid is an acid that can ionize only one H plus ion. Dibasic can ionize two. Tribasic can ionize three, and so on and so forth. It's just like when we talk about the conjugate acid of a base and then the conjugate base of an acid. Remember, the conjugate acid of a base is a species form when the base accepts the proton. Then the conjugate base of an acid is a species form when the acid donates a proton. You see that kind of mix, interchanging things. It's the same theory here. So we have acidity of a base, we have basicity of an acid, then we have acidity of a base. This one is the number of ionizable OH minus ions present in an alkali. So sodium hydroxide is monoacidic. Explain or define the term monoacidic base and give examples. What is a monoacidic base? And give an example. Oh, a monoacidic base is a base that has only one ionizable OH minus in it. Example: sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium hydroxide is not. Calcium hydroxide is diacidic base. Calcium hydroxide, barium hydroxide, magnesium hydroxide, iron 2 hydroxide, copper 2 hydroxide. Those are diacidic bases. Why? Because they are bases that have two ionizable OH minus ions in them. What is acidity of a base or acidity of a base is a number of ionizable OH minus ions within the base. What is basicity of an acid? Or basicity of an acid is a number of H plus ions, ionizable H plus ions within the acid. Ionizable means like can be converted into ions. Okay, that's what it means. Ion, ionizable, meaning it can be changed into ions. Then another term we'll talk about is what we call amphiprotic substances. These are all terms you can be asked to define and give examples. The twin brother for this is amphoteric. There are two different things. A substance that can act either as a proton acceptor or a proton donor. Did you see what I said? I didn't say can act as an acid or can act as a base. A substance that can act either as a proton acceptor or a proton donor. It can act as a proton acceptor or a proton donor. It's called an amphiprotic substance. All amphiprotic substances contain a hydrogen atom. All of them. You need to take note of this. And that's one difference between amphiprotic and what we call amphoteric substances. All I was drawing a line. All amphiprotic substances contain hydrogen atoms in them. So one example is water. Here in this equation, water is accepting a proton from HCl. Water is acting as a base. In the second equation, the same water, but here water is donating a proton to ammonia. Here water is acting as an acid because it's donating a proton. Water, therefore, is an example of an amphiprotic substance. Define amphiprotic substance, give 2 examples, and write chemical equations to support your examples. Water, let it donate 1 proton to HCl, for instance. Let it accept 1 proton from a, you can even accept the proton from, you can write another one for it accepting a proton from HCl, the same HCl. In that case, you have, you know, oh no, you can't write an equation for it donating a proton to HCl. It'll be difficult for you to write that equation. Like you'll be getting something like H2Cl plus. No, that's ridiculous. So you choose another compound that you can donate a proton to. In fact, you can even choose water itself, water plus water. You give you hydrosonium ion plus OH minus. Okay. Did you hear what I said? An amphiprotic substance is a substance that can act either as a proton acceptor or a proton donor. Okay. I didn't say can act as an acid or a base, or I didn't say that. Or can react with an acid or a base. Like you don't even see these definitions in books. What you see in books, most books, is amphoteric, and that's another term. What is amphoteric substance? An amphoteric. Oh, okay. This is another example of a amphiprotic substance, bicarbonate. The bicarbonate ion here, the bicarbonate ion. In this first equation, the bicarbonate ion is accepting a proton from hydrosonium ion. But in the second equation, it is donating a proton to OH minus. Another example is hydrogen sulfate ion. In the first equation, it is accepting a proton from hydrosonium ion. In the second equation, it is acting as a proton donor, donating a proton to OH minus. You see, you can create your own amphiprotic substance. Did you realize that? You can create your own amphiprotic substances. You can create a substance, you can have a substance and force it to donate a proton in one reaction and force it to accept a proton in another reaction. That substance becomes amphiprotic substance. I think you realize that, right? Yeah. But the second one, they are specific substances. They are no, you can't create your own. They are well demarcated substances or compounds we call amphoteric compounds or substances. They are well known, we know them. They are compounds that can react as either an acid or a base. Did you see the difference? Amphiprotic substances, they can act either as proton donors or as proton acceptors, and they always contain hydrogen in them. In amphoteric substances, they are compounds that can react. They react as either an acid or a base. Or some will say they react with both acids and bases. That's acceptable. So one compound, in one reaction, it can react with an acid. In another reaction, it can react with a base. And I said they are well-known compounds. One of them is zinc oxide. Zinc oxide. Another is zinc hydroxide. So we have the oxides and then the hydroxides. Sometimes the question will ask you to write 2 examples of oxides that are amphoteric, or give 2 examples of amphoteric oxides. In that case, you can't write zinc hydroxide, you'll be wrong. Zinc oxide is what you can write. You can write aluminum oxide. You can write lead oxide, lead 2 oxide. The oxides are aluminum oxide, lead 2 oxide, tin oxide, and then zinc oxide. Then the hydroxides, you have again zinc hydroxide, you have aluminum hydroxide, you have lead 2 hydroxide, but we don't have tin hydroxide, but we have water too. All of these substances can act as either an acid or a base, or they can react with an acid or can react with a base. Now, the reaction of zinc oxide with an acid, hydrozonium ion denotes an acid. See what is happening? It gives you zinc plus water. You need to learn some of these reactions. In the presence of hydroxide ion, in the presence of a base, with the hydroxide ion serving as a base, you actually need water. You need water. It gives you a compound we call the zincate ion, where you have zinc, four moles of hydroxide. Those are complex ions. Zinc tetrahydroxy. No, tetrahydroxy zinc ion. Okay, commonly called the zincate ion. Then water also acts as amphoteric. Remember, water also acts as amphiprotic. It can also act as amphoteric. It can react with an acid, as you can see. HCl is the acid. Here it is acting as a base. Water is acting as a base. And then it can, so look at the products. It forms hydrozonium ion and HCl. Here it's just the same as donating a proton, or accepting a proton rather. So it's acting as a base here. Here it's acting as the acid, and it's the same as donating a proton to ammonia, okay, which is a base. Then we have hydroxide, aluminum hydroxide reacting with HCl. So aluminum hydroxide is acting as a base, and then reacting with OH minus. Then aluminum hydroxide acts as the acid. It forms aluminate ion, AlOH4, then minus one at the top there. It's called aluminate ion. Tetrahydroxy aluminate ion. That's how it's called. Tetrahydroxy aluminate ion. All right. That's all for amphoteric substances. And this is where I will be bringing the class to an. And when we meet again, we'll talk about strong and weak acids and what are they. And then we can take that from there. But that's where this is where I will end. If you have any question, please ask. I have given you the notes. I said that already. I've given you, I think, the Word document form of the notes. The full note on acid, base, and salt is in the Google Classroom. You can have access to it. All these things are in it. But maybe I'll post it again. I don't know whether it's possible. I don't know. Maybe it's not possible for those who join the class later to have access to things that were posted earlier. So one of these days, I'll have to post the notes again so that those who join the class after I had posted it, but are unable to go back and have access to it because of however the system is, can also get access to it. People, do you follow anything at all? You don't have any question for me? Okay, if you have no question, I think I have a question for you. What is the difference between an amphoteric, or give me two differences between amphiprotic and amphoteric compounds? Highball, Maxwell. You are on and off. When you like, you come. When you don't like, you don't come. Jasper, Kuma.
Stay.
Yes.
So please, amphoteric substance, they can react either as acids or bases, but
Jasper, you didn't finish talking and you muted yourself. Amateur carriage. What's the difference between amphiprotic and amphoteric compounds? Jason Awaga. Okay. Okay. Yeah, carriage, go on. Amateur carriage, go on. Hey, you people, are you people in Ghana or you people are somewhere else outside Ghana? Eh? Your networks are so bad. Meanwhile, we are all in Ghana. There are times I know the network is completely bad, but I don't think, unless you people are not hearing me. Tenu carriage, can you hear me? What's the difference between amphoteric and amphiprotic substances?
Sir, amphiprotic substance is a substance that acts as a proton acceptor or as a proton donor. And whilst an amphoteric substance is a substance that can react as either an acid or a base.
All right, that's correct. Yes, Theophilus Sebuabe.
Sir, please, I want to ask a question.
Ask.
That's are all amphiprotic substances amphoteric?
No, not at all. The amphoteric substances that I gave you specific examples. Those are well-known examples of amphoteric substances. And one other difference between them is that you see not all those compounds contain hydrogen. Let me go back to that slide. Amphoteric, look at them. Yeah, there they are. Not all of these compounds contain hydrogen. Not all of them contain hydrogen. Zinc oxide, tin oxide, lead oxide, especially the oxide, they don't contain hydrogen. But if you are hydroxide, certainly you contain hydrogen. But for amphiprotic substances, you must necessarily contain hydrogen to be called amphiprotic. That's another difference between them. All right, good afternoon, ladies and gentlemen. The last time we stopped at amphiprotic substances, I remember, and I said they are those substances that are capable of acting as a proton acceptor or a proton donor. We did all of these things. I gave examples of them. Then we looked at amphoteric substances. And I said they are compounds or substances that react either as an acid or a base, or they react with both acids and bases. That's another way of putting it. Examples are zinc oxide, zinc hydroxide, water. Water is both amphoteric and then amphiprotic. Aluminum hydroxide, aluminum oxide, lead-2 oxide, lead-2 hydroxide, and tin-2 oxide. These are well-known amphoteric substances, very, very few of them. So in an examination, if you're asked to give 2 examples of amphoteric substances, or examples of amphoteric substances, it is these ones that you are giving. It is these ones that you are giving, okay? Very few amphoteric substances: zinc oxide, zinc hydroxide, water, aluminum oxide, aluminum hydroxide, and so on and so forth. Today, let's look at strong acids and weak acids. What's a strong acid? It's a man who taught you this, I believe. Daniel Ewoyi, what's a strong acid? When do we say an acid is strong and when do we say it is weak? Bisa, Nana Kofi. If you can hear me, unmute your videos.
Say,
Yes.
a strong acid
Who is talking?
is an acid that Daniel, how are you?
Okay.
A strong acid is an acid that ionizes completely in a solution.
Okay. A strong acid is an acid that ionizes completely or dissolves completely in water or in aqueous solution. I said you should all unmute your videos. I want to see your faces. If you don't unmute your video, what it means is that you are not by your device. You've just come to set up and then you're going to do something else. Atikese, Bisa, Jason Awaga, Jasper Kuma, Ajima Lawe. I said you should all leave your videos on. I want to see your faces. I'm at your courage. If you are hearing, you didn't even connect your video at all. Please connect it. You just connected your sound. Connect your video and leave it on. I'm at your courage. But what I told you people have in your faces that sometimes you don't just see your faces. Okay. So there you go. A strong acid is an acid which dissociates completely in water. That is, all the acid molecules break up. Courage, your hand is up. I'm at your courage. Okay. Your mic is unmuted. I don't know why. I mean, you can't talk. Now, because strong acids break down completely in solution, the concentration of hydrogen ions that is produced is the same as the concentration of the acid, the original acid. Because every, acidity is determined by H plus ion. Every H plus ions or every hydrogen in the acid is converted into H plus for strong acids. So an example is nitric acid, completely dissociates in water. It gives you H plus aqueous plus NO3 minus aqueous. Now, strong acids have pH between or from 1 to 3. If your pH is 1, 2, or 3, you are a strong acid. If your pH is between 4, from 4, 5, 6, then you are a weak acid. Strong acids dissociate completely in water. Weak acids dissociate partially. That's the difference. That's just the difference. Strong acids dissociate or they ionize completely. When we say something ionizes, meaning it becomes ions. It is converted into ions. I said your videos should be on. That's what I said. Everybody's video should be on. Uma Jasper. I said your videos should be on. Okay. I think I said no Bisa. So meaning Bisa is not by his device. That's what it means. Bisa in Kuma Jasper. You just came to set up your phones and then you went about probably doing your own thing. Okay, Jasper is on now. What has taken you so long, Jasper?
Sir, please, nothing.
Okay. So that's about Jasper. What's the difference between a strong acid and a weak acid? Jasper, unmute your mic. Kuma Jasper, can you hear me? Atikese Iris, what's the difference between a strong acid and a weak acid?
Say a strong acid dissolves completely in water, whilst weak acid dissolves partially in water.
Excellent. Excellent. Okay. The whole of the chemistry, there are only 7 acids that are strong. There they are on your screens. These are the only 7 strong acids we have in chemistry. All other acids apart from this are weak acids. HCl, HBr, HI, HCl called hydrochloric acid, HBr called hydrobromic acid, HI called hydroiodic acid. Then we have HClO4. The common name is perchloric acid. You can give the IUPAC name, tetraoxochlorate 7 acid. That will be the IUPAC name. Then we have its twin brother, HClO3, called the chloric acid. That's trioxochlorate 5 acid. Then we have H2SO4. Sorry, these two, I thought I corrected this. It's supposed to be, you should know this. It's supposed to be written as a subscript, not the way it is here. H2SO4, that's sulfuric acid, and HNO3, nitric acid. These are the only strong acids we have in chemistry. There are only 7. There are only 7 strong acids in the whole of the chemistry. All other acids apart from this are weak. Now, within a series of oxy acids, okay, oxy acids or oxo acids. You remember oxo acids in core chemistry? We look at oxo anions, then we look at oxo acids. Okay, they are the same as oxy acids. The ions within a series of oxy acids, the ions or the compounds or the molecules with the greatest number of oxygen molecules or oxygen atoms are the strongest. For example, nitric acid is stronger than nitrous acid. You see, nitric acid is HNO3. Nitrous acid is HNO2. That's nitrous acid. That's a common name. And we are saying that nitric acid has more oxygen atoms than nitrous acid. You can see that nitric acid has 3 oxygen atoms. Nitrous acid has 2. So nitric acid is a stronger acid than nitrous acid. In fact, nitrous acid is a weak acid. It's not even among the 7 strong acids I've given you. Perchloric acid is stronger than chloric acid, which is also stronger than chlorous acid. That's dioxochlorate 1 acid, and then that's a chlorate 1, chlorate 3, and then it's also stronger than hypochlorous acid. That's the monoxochlorate 1 acid. So you have HClO4 stronger than HClO3, also stronger than HClO2, which is also stronger than HClO. You can see that the strength of the acid increases with increasing number of oxygen atoms, or in other words, the strength of the acid decreases with decreasing number of oxygen atoms for acids within the same series of oxo acids or oxy acids. And you can see that it's just the first 2 that are actually part of the 7 strong acids. HClO4 is a strong acid. HClO3 is also a strong acid. You see them among the 7 I've given you at the top here. Okay. Then HClO2 is a weak acid, but it's also stronger than HClO, only because it has more oxygen atoms than HClO. So going by the same inference, you agree that H2SO4 will be stronger than H2SO3. H2SO3 is also an acid, but H2SO4 is stronger. In fact, you see H2SO3 is not even part of the strong acids I've given you. It's a weak acid. That is very important. You need to take note of this. Absolutely important. As the number of oxygen atoms within the acid increases, the strength of the acid increases. For acids that belong to the same oxy acid series, it's important you take note of this. All right. So I made a point that apart from these 7 acids, okay, or in the absence of these 7 acids, any other acid is a weak acid. Yeah, you notice that I didn't put HF here, hydrogen fluoride. Hydrogen fluoride is not a strong acid, it's actually a weak acid. HF, it's a weak acid. So all the other acids, carbonic acid, phosphoric acid, hydrogen sulfide, that's H2S, you know, so all of them are weak acids, together with all organic acids. All organic acids are weak acids. Dorcas, can you hear me? Now, the majority of acids exist as weak acids. I made that point already. if the whole of the chemistry we have just 7 acids are strong acids, you can just imagine. Majority of the acids in chemistry we have exist as weak acids. What are they? They are the acids which dissociate partially in water. Okay, Iris gave that definition earlier. Weak acids, they dissociate partially, or they ionize partially. They dissociate incompletely in water. All organic acids like acetic acid and some inorganic acids are weak acids. All organic acids are weak. Acetic acid, citric acid, palmitic acid, and all of them. Lactic acid, okay, all of them are organic acids. They have their chemical formulae. All of them are weak acids. In addition to some inorganic acids like carbonic acid, H2CO3, like phosphoric acid, H3PO4, like hydrogen sulfide, H2S. All of them are weak acids. Now, since their dissociation is only partial, it is depicted by double half arrows. So you see this equation here. Because the dissociation of weak acid is only partial, we use the double half arrow, what we call the equilibrium sign, to write that equation for weak acids. What it means is that there's always an equilibrium between the unionized part of the acid, which is the one that has not ionized, and then the very few that have ionized. So that anybody who sees that process, it looks as if the ionized parts are combining to form back the unionized part, the original acid. So we use equilibrium sign to indicate the dissociation, to write the equation for the dissociation of weak acids. It's important you take note of this. So the double arrows indicate here that one, the aqueous solution of hydrofluoric acid not only contains H+ ion and F- aqueous ion, but also the undissolved or the undissociated acid HF. Okay, I explained that. There's an equilibrium between the undissociated acid HF and the ions furnished by it. That's the H+. All right, folks, I'm back, sorry. Now, on the average, only about 1% of a weak acid solution dissociates in water. Can you imagine that? If you take a weak acid, just about 1% of it dissociates. That's 0.01. Just about that dissociates. Therefore, the concentration of hydrozonium ions in a weak acid solution is always less than the concentration of the dissolved acid. That what I mean by the dissolved acid is the acid you are trying to dissolve. Okay, so for weak acids, the concentration of the H+ ions or the hydrozonium ions that are produced is always less than the concentration of the original acid. That's what it means. It's always less, but that dissociation is so small. We say it is negligible, that sometimes we say that dissociation does not even affect the concentration of the acid at all. Okay, you need to remember this because when we come to calculations of what we call pH of strong acids and weak acids, this concept, comes to play over there. Now, okay, examples of weak acids are HF, that's hydrofluoric acid, CH3COOH, that's ethanoic acid, what we call the acetic acid. We have a C6H5COOH, that's what we call the benzoic acid. These are organic acids. And then we have HCN. That one is not an organic acid, it's an inorganic acid. We call it the hydrocyanic acid, hydrogen cyanide, hydrocyanic acid. Now, strong bases and weak bases do not require additional explanation, do they? No, the concept is the same. So strong acids, strong bases will ionize completely in aqueous solution, whereas weak bases will ionize partially, just like for the acids. Strong acids ionize completely, weak acids ionize partially. The concept is the same for bases. Strong bases ionize completely, weak bases ionize partially. Okay. Now, the conjugate of a strong acid or base is very weak. But the conjugate of a weak acid or base is not necessarily strong, but most of the time is strong. I explained this concept when we did the conjugate acid base pair. You remember? I explained this. Common strong bases are the hydroxides of group 1 and most group 2 metals, but not most, I think all of them. We have only 7 strong acids. For the bases, the hydroxides of group 1 and group 2 metals, they are the only strong bases we have in chemistry. All other bases are weak bases. You see what I'm teaching you? Very important things I'm teaching you. I'm telling you. So you go to an examination, they ask you to give 2 examples of strong acids and weak acids, 2 examples of strong bases and weak bases. Then you are like, you don't know what you are writing. The group 1 and group 2 metal hydroxides, they are the strong bases, that's all. Lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, francium, calcium, strontium, barium, where beryllium is not here. Then we have magnesium. These are group 1 and group 2 metal hydroxide. They are the only strong bases we have. All other bases, apart from this, they are all weak. Aluminium hydroxide is a weak base. Boron hydroxide is a weak base. Iron 2 hydroxide, iron 3 hydroxide, zinc hydroxide, copper hydroxide, whether copper 1 or copper 2, all of them, they are weak bases. Strong bases have pH 12, 13, and 14. Weak bases have pH 8, 9, 10, 11. You know the pH scale, you are very familiar with that. From 0 to 14, the middle, 7, is neutrality. If you are from 7 not included, 7 downwards, that's acidity. From 7 coming to 0, that's acidity. Earlier on, we said if your pH is 6, 5, 4, you are an acid, but a weak acid. That's the range for weak acids. If your pH is 3, 2, 1, you are an acid and very strong one. when you come to the bases, as you move from 7 towards 14, basicity increases, strength of alkalinity or basicity increases. So pH of 8, 9, 10, 11, you are a base, all right, but you are a weak base. 12, 13, 14, you are the strong base. Okay, so that's about, I've explained that term, what a strong acid is and what a weak acid is, what a strong base is and what a weak acid, a weak base is. You take your past questions, you see students being asked to define or explain those terms. Differentiate between a strong acid and a weak acid, I've explained that, and give examples. Or differentiate between a strong base and a weak base and give examples. I've explained that. And know that when you sometimes they ask you to write equations to support that. Note that when you are writing the equation to show the dissociation of a weak acid and of a weak base, we use the equilibrium symbol, the equilibrium sign, because that dissociation is not a complete dissociation. There's always an equilibrium between the unionized part of the acid or of the base and the ionized part. So equilibrium sign is used to depict that. Then another term is concentrated acids and then diluted acids. I started by saying that acids and bases that are strong are not necessarily concentrated. So sometimes another term they ask students to differentiate between is a strong acid and a concentrated acid. Many times you think if an acid is concentrated, then it is strong. Or if an acid is strong, then it must be concentrated. No. Concentration has nothing to do with strength of the acid. It has nothing. Concentration is what is the amount of the acid present in a specific volume of water. That's what defines concentration of the acid. It is not the same as strength of the acid. So I said concentration has nothing to do with the ability of a substance to dissociate. Furthermore, polyprotic acids are not necessarily stronger than monoprotic acids. My question is, what are polyprotic acids? What are monoprotic acids? Precious Mawina, what did we say are polyprotic acids? Ajima Lawe.
Say a polyprotic acid is an acid which contains many or a lot of acid molecules per amount of water or liquid fluid.
Okay, you've tried, but I don't think that's what I told you. Maxwell Highball. Yeah. Maxwell, go on. Maxwell, can you hear me? I can hear you. Go on. Okay, Maxwell has a problem with you have a problem with the earpiece you are using. Jason Awaga, what's a polyprotic acid and what's a monoprotic acid? What's the difference? Jason Awaga. Bisa Nana Kofi, are you by your phone now? I'm a mature.
Service, yes, it was just the connection. Hello, Service, can you hear me?
I can hear you. Lisa, I can hear you. Go on.
Okay. I'm saying it's a polyprotic acids are acids that have more than one ionizing H plus atom in their molecules, and then one ionizing H plus atom per their molecule.
Okay, I will accept that somehow. Yeah, polyprotic acids, they ionize more than one H plus ions. Okay, whilst monoprotic acids are those that ionize just one H plus ion per molecule. That's correct. Now I'm saying that polyprotic. So okay, examples of polyprotic acids. Theophilus Sebuabe, give me an example of a polyprotic acid.
Say phosphoric acid.
And that one is specific.
PO4.
And that's specifically called what?
Phosphoric acid.
And that's specifically what type of acid under the polyprotic family?
It's a triprotic acid.
That's a triprotic acid. All right. So under the polyprotic, remember we have the diprotic and then the triprotic. Now, that's good. The point I'm making is that polyprotic acids are not necessarily stronger than monoprotic acids. No. If the acid is a strong acid, it is not because of the number of H plus ions that is in it. So that you say, oh, sulfuric acid is a strong acid. HCl is also a strong acid. But sulfuric acid has two H plus or two hydrogen atoms in it. So it is stronger than HCl. No, there's nothing like that. There is absolutely nothing like that. All of them are strong acids. It doesn't mean they have the same pH, but their pH will fall within the pH for strong acids, like from 1 to 3. That's the point I'm making. Polyprotic acids are not necessarily stronger than monoprotic acids. No. All right. Now, I said concentration is also different from strength. Now, what's the meaning? The strength of an acid, so what's the difference? The strength of an acid is a degree of dissociation of the acid in solvent. The greater, hold on. Remember I said I said strength of an acid. I'm not saying strong acid or weak acid. A strong acid dissociates partially, dissociates completely or fully. A weak acid dissociates partially. The strength of an acid is a degree of dissociation of the acid. You understand? Strength of the acid is the degree of dissociation. If that degree of dissociation is complete, then we say it's a strong acid. If that degree of dissociation is partial, then it makes the acid a weak acid. So the point I'm making is that strength of an acid is not the same as the concentration of the acid. There's no relationship between strength and concentration, so that we say strong acids are more concentrated than weak acids. No, they are two separate terms. The concentration of an acid is the amount of the acid, the number of moles of the acid dissolved in a DM cube of the solution. That's concentration of the acid. And concentration, we can say the solution is concentrated, or the acid is concentrated, or is dilute. If the acid is concentrated, it means there are more amount of the acid in small volume of water. And if the acid is diluted, then we say there is small amount of the acid, moles of the acid in large volume of water. So the acid is diluted. We can also say that a concentrated acid is the acid that has no water added to it. Whilst a dilute acid is an acid that has water added to it, because dilution is about addition of water. So if the acid is concentrated, it doesn't mean that it is not in the aqueous form. If it says concentrated, then some of you think is thick, like solid, like condensed milk. No, that's not necessarily what it means. When it is concentrated, what it means is you don't have a lot of water. You have large amount of the acid, most of the acid in small volume of water. So it's highly concentrated. If it is diluted, it means more water has been added to it. That's just the meaning of those two terms. So strength of an acid is the degree of dissociation of the acid in a solvent, whereas the concentration of the acid is the amount or most of the acid dissolved in a DM cube of solution. I've explained the difference between a strong acid and a weak acid, a strong base and a weak base. I've also explained to you the difference between strength of the acid and the concentration of the acid. I said they are not the same thing. And I've also explained to you the difference between a dilute solution or a dilute acid and a concentrated acid. A dilute acid has more amount of water molecules with very small amount of the acid dissolved in it. Whereas a concentrated acid has small amount of the acid dissolved in large quantity of water, large volume of water. And I said you can also explain it in this way, that a dilute acid is an acid that has more water added to it, whereas concentrated acid is an acid that has no amount of water molecules or only small amount of water molecules added to it. So that brings us to the end of that aspect. What a strong acid is, what a weak acid is, and so on and so forth. The next thing we are going to look at is properties of acids and bases. And then once we finish properties of acids and bases, then we'll begin salts. Okay, we'll look at salts and other things. And once we finish salt, before we delve into the calculations, I'm not even too sure whether we should do the calculations, since that's what Mr. Manso always talks about the calculation aspect more than the theory. So I'm teaching you the theory, the non-calculation aspects of the things that you probably may not have spoken about. The properties of acids, you know them. They have sharp, sour taste. Their taste is sour and sharp. In that sour is just like if something is sharp, is sharp. You see when you put the good lemon juice. When you put lemon juice into your tank, you just drop it on your. Do you see how you feel? You feel some sharp. The taste is sharp. Is distinguishable. You can distinguish between it. It's a sharp, clear taste. It's just like when you use your tank to touch the back of a battery. Not the back of the battery. They're actually the pole, the north pole or the positive pole of the battery. You see how you see what you feel on your tank. You feel some sharp taste. Okay, as if something has shocked you in the case of battery. That's how the taste of acids are. If you have ever tasted lime, you get a feel of what I'm talking about. Acids have that taste. We describe that taste as sharp and sour. And they are smooth or neutral, not slippery between the fingers. If you drop an acid in your finger, maybe the index finger, and then you rub the thumb finger on it, it will not be slippery. Okay, you feel it's very smooth. You feel smoothness between the fingers. The 10 blue litmus paper red. Now, some people have argued that this property ought to be a chemical property. I said no. It's a physical property because these are things you actually see. This is something about the things. It is about acids. Chemical properties really is about chemical reactions. Now, they are highly corrosive with pH less than 7. All acids are corrosive. with pH less than 7, of course, you know that acids are highly corrosive. Acids are highly corrosive, and the concentrated ones are more corrosive than the dilute ones. The concentrated ones, meaning water has not been added to them. They are more corrosive than if you add water to them. Okay, if you dilute them, you reduce their strength. You reduce their concentration. You reduce their concentration, not their strength. So its corrosive ability is reduced. Weak acids also corrode. All acids corrode. All acids are highly corrosive, whether it's a weak acid or not, it corrodes. Now, strong acids conduct electricity strongly in solution. Example, H2SO4, HCl, HNO3. Why is it that strong acids conduct electricity strongly in solution? Why is it so? I think the next point will be weak acids conduct electricity poorly in solution. Why is it so? What do you think, Jasper Kuma? Sebo Abetubulus.
So this because they have a delocalized electron.
No. Nkunu Frank.
Say because they dissolve completely in water, or they dissociate completely in water.
Who is talking?
Say Tiflos.
Okay. All right. I'll take the second one. Now, strong acids, ionize completely in water. Conductivity of electricity is by movement of ions, okay, or electrons, but in this case, ions. Conductivity of electricity is by movement of ions. So the more ions you have in solution, the greater the degree of conductivity, or the higher the conductivity of that solution. So since strong acids dissociate completely, meaning they have more ions, they produce more ions, more H plus ions, and then the negative ions in solution to be able to conduct electricity. So the conductivity of electricity is very strong compared to the weak acids, because they produce very few, or they produce fewer ions. Why? Because they ionize partially, not completely. So the point I'm making is that if you dissolve HNO3 in water and you you connect a circuit to it, to a bulb, you can just put a wire into it and connect to a battery, and then connect to a bulb, so that current passes through the HNO3 solution. Okay, connect two live wires, or put two live wires, okay, conduct electrical wires into the solution. Then to one end, put the batteries over there. Then tie a bulb. When we're young, those things we've been doing. Tie a bulb to the second one, the end of the second one. Then use the bulb to touch the battery. You do that for a strong acid, and you do that for a weak acid. You see that the bulb will the bulb will be brighter. The light will be brighter in the strong acid than you see in the weak acid. Weak acid like carbonic acid or H2S. So these are some of the physical properties of acids. I've given you 6. They have a sharp sour taste. They turn blue litmus paper red. They are smooth or slippery, not slippery between the fingers. They are highly corrosive with pH less than 7. Strong acids conduct electricity strongly in solution. Weak acids conduct electricity poorly in solution. These are things you can write. for very good marks in examination. Okay, there is one at the bottom, the 7. Acids turn methyl orange, pink, or red, and phenolphthalein to colorless. These are two what we call indicators that we use in what we call titration work. Indicators are they are like dyes. They are dyes that are actually obtained from plants that change color in a medium depending upon the pH of the medium in which they are put. Litmus is also an indicator. Litmus paper is also an indicator because when you put it in a medium, it changes color depending upon the pH of the medium in which you put it. So it's also an indicator. Litmus paper, that's what I mean. There are others like methyl orange. It's also an indicator. The color is just orange. It looks orange. When you put methyl orange into an acid, or if you have an acid and then you drop methyl orange into it, okay, the pink color, or the orange color of the methyl orange will disappear. You see a pink or red color. Or in other words, the acidic solution, which is colorless, will turn pink or red. That's the point I'm making. That's the point I'm making. Then to phenolphthalein, it is colorless. Phenolphthalein is colorless anyways. If you drop it into an acidic solution, you still see a colorless solution. But normally in titration, what happens is that the indicator is dropped into the base. If you put a phenolphthalein into any basic solution, you see a pink or red color. Yeah. Is it pink or red? Yeah. Yeah, you see a pink or red color. And then when you release the acid from the burette onto it, the solution becomes acidic. All of a sudden, the pink color disappears, and then you see a colorless color. The solution becomes clear. No, you will not see any color again. That's what we call the end point of the titration. The point I'm making is that anything that's an acid has some coloring effects on these two indicators. For methyl orange, acids will turn methyl orange to pink or red, and they turn phenolphtalene's color to colorless. Take note of that. Then bases, the same physical properties of bases. They taste bitter. Bases taste bitter. You feel a bit of bitterness in lemon and the rest, but that's not what we are talking about. What you actually feel in lemon, okay? The first thing you feel in your mouth or in your tongue, when you just put a drop of lemon on your tongue, the first thing, your mouth feels something. That's a sour and sharp taste we are talking about. It's different from bitterness. Bitterness is different from bitterness. Bases, they taste bitter. Sodium hydroxide solution, when you put it into your mouth, is bitter. FFM, bitter. You feel it. It's bitter. Then they are slippery between the fingers. They turn red litmus paper blue, just the opposite of the acids. The acids turn blue litmus paper red. In fact, I forgot one thing. Let me add it. They don't just turn red litmus paper blue or blue litmus paper red. I almost forgot this. I didn't see it early. They turn wet blue litmus paper red or wet red litmus paper blue. The litmus paper has to be wet, or we say damp. You damp the litmus paper or you wet it, meaning put it into water. Just dip the litmus paper into water before you put it into the acid. Let it be wet. If the litmus paper is not wet, nothing will happen. Put the blue litmus paper into the acid, the color will still be the same. So the word is wet. They turn wet. They turn wet red litmus paper blue. It's very important. And then the acids to the turn wet blue litmus paper red. The paper has to be wet. It's important. So you are asked to explain. In other words, it has to be in the aqueous form, okay? Because once you put it into water, you are making it wet. You are making it in the aqueous form. You have to explain. They said the litmus paper, the blue litmus paper was put into an acidic solution, but there was no change. There's no change in color. What could account for that? What's the possible explanation for that? Well, the litmus paper was not made wet. Okay, the litmus paper reacts with the acid only when it is in the aqueous form. The red litmus paper reacts with the base only to turn its color to blue, only when it is in the wet form, in the aqueous form. Otherwise, nothing will happen. Then they turn methyl orange indicator to orange or yellow, and phenolphthalein indicator pink. So I explained this. For methyl orange, for what we call titration, methyl orange is actually orange or yellow in color. When you drop it in a base, it is in the base that we actually drop it first. The base is in a conical flux. When you drop it, it will just give its color. The base is colorless, plain. When you drop the methyl orange into the base, the methyl orange will just give its color to the base. Add the color, add the base, so the base will become orange. That's what I mean. That. So if you put methyl orange into any basic solution, the color will be orange. Okay. But remember, when you put it in an acidic solution, so during titration, that orange color is turned to pink or red at the end of the titration. Then the solution has become acidic because you have released acid from the burette. Then phenolphthalein, its color is, it has a colorless, it has no color, it's colorless. When you drop phenolphthalein into a base, which is also colorless, it gives the base pink color. The color changes all of a sudden to pink. None of the two things is pink in color, but all of a sudden you see a pink color. Then when you release the acid from the burette onto it, what's the end color? The end color will be colorless. If you remember what I just said, for acids turn phenolphthalein colorless. First, it is dropped into the base, and the base gives it, or it gives the base a pink color. Then at the end point of the titration, the color becomes colorless, or it has no color. You need to know the color of these indicators, these two particular indicators, phenolphthalein and methyl orange, in both acidic medium and in basic medium. That's what I've just told you. In acidic medium, phenolphthalein is colorless. In basic medium, it is pink. In acidic medium, methyl orange is pink or red. In a basic medium, it is yellow or orange. Strong bases, just like strong acids, conduct electricity strongly. Sodium hydroxide, potassium hydroxide, and calcium hydroxide are examples. I've already told you that the group 1 and group 2 metal hydroxides, they are the strong or the strongest bases we have. All other bases are weak. Weak bases conduct electricity poorly. Example, ammonia. Ammonia is a good base, but it's a weak base. It's one of the commonest bases we have in the laboratory. We have sodium hydroxide too. It's also a base, but it's weak because it's not part of the strong ones I gave you. Then they have pH greater than 7. All bases have pH greater than 7. If you are weak, yours will be 7, yours will be 8. That is not to say that 7.5, for instance, is not a base. It is. Okay, I just use the whole numbers. So if you have a pH of 7.1, you are not neutral. pH of 7.2, you are not neutral. You are actually basic, but you are all a weak base. is 8, 9, 10, 11, you are all weak. Then from 12, 13 up to 14, they are strong bases. All of them have pH greater than 7. So that's about the physical properties of acids and bases. Now let's look at the chemical properties of acids. And you should be able to write some of these properties down. You go to an examination and they say give 2 physical properties of acids and bases, and you tell me you can't write that down, then I'm sorry for you. Plenty, I've given you 7. Chemical properties. 1, reaction with metals. That's what I mean. Acids or metals above copper in the reactivity series will react with acids to give off hydrogen gas and a salt. Do you know the reactivity series? Do you remember the reactivity series? What is also known as the electrochemical series? We say Kwame Nkrumah can marry all common Zambia females simply provided he could have silver, gold, and platinum. So Kwame Nkrumah, that potassium is the first one, that's Kwame Nkrumah, and that's Kwame. Sodium is the next, that's Nkrumah, followed by calcium, can marry magnesium, or aluminium, common, carbon. Carbon is actually not a metal, but it's included for a reason. Common, carbon, Zambia, Zn, that's zinc. Females, Fe, iron. Simply is what? Sn, tin. Provided, Pb, lead. He, that's H, hydrogen. Hydrogen is also not a metal, but it's also included in the reactivity series for a reason. Could, that's Cu, copper. Half, that's Hg, mercury. Silver, that's Ag. Gold, that's Au. And platinum, Pt. This is what we call the reactivity series. Okay, I know Mr. Mansu gave you this and even gave you one series for the release of ions during electrolysis. This plays a role also in electrolysis. Then he gave you one for ions, the anions. I've just forgotten that one. I think Jasper and Co taught me some time ago. Jasper, do you remember the chlorine minus, iodine minus, SO4, OH minus? OH minus is actually the last one. Jasper, do you remember the song? Jasper or Dorcas, Vule? Who remembers the song Mr. Mansu taught you about the anions? Oh, nobody is hearing me.
Sir, I've forgotten.
But why are your this is muted again? I said you should leave your cameras on. Why do you put them off? Courage.
Sir.
What's the song?
I remember.
Yeah.
Oh, in Britain, children can never suffer. So O is OH minus in Britain. in is I minus. In breathing is Br minus. Can is CO3 2 minus or Cn minus.
It's Cn minus. Cn minus. Can is Cn minus.
Is that
Can is Cn minus.
Yes, can is Cn minus or CO3 CO3 2 minus. Either one of them.
So you
That's
said,
what you.
oh, okay, come again.
And
Come again.
In breathing, children can never suffer.
So which one is a okay? All right. Children is a Cl minus.
Yes. And
Can is the Cn minus. That's cyanide.
yeah.
The never is
NO3
minus. And the suffer is SO4.
SO4 minus or SO4 2 minus or
SO3 2 minus.
SO3 2 minus.
Excellent. Yeah, that's correct. That's it. Doctors, you remember now. You people taught me this song, but you forgot. Oh, in breathing, children can never suffer. Yeah, that's the order. That's actually a decreasing order of ease of release. OH minus is easily released first if it is available, followed by iodine, followed by bromine, followed by chlorine, followed by cyanide, then NO3, and then SO4 or SO3 is the last one. Okay, so for the cations, okay, the song is Kwame Nkrumah can marry all common Zambia females simply provided he could have silver, gold, and platinum. It's important all of you know how to sing this song because it has implications for redox reaction, for electrolysis, for for what we call reactivity of metals. Okay, so you have to explain why, for instance, iron cannot be protected. Iron cannot be protected by electroplating it with tin. Explain why you can't protect iron by electroplating it with or coating it with tin metal, but rather with zinc metal. Because if you are above your friend, you are more reactive than your friend. So if you are protecting somebody, you should be more reactive than the person you are protecting. But if the person you are protecting is more reactive than you, then you can't protect the person. Okay, let me take the song again. I hope you are writing it down. This is the last time I'm singing it. I said Kwame, that's for K, potassium. Nkrumah, that's Na, sodium. Can, that's Ca, calcium. Marry, Mg, magnesium. Or, Al, aluminium. Common, C for carbon. Zambia, Zn for zinc. Females, Fe for iron. Simply, Sn for tin. Provided, Pb for lead. He, just H for hydrogen. Could, Cu for copper. Have, Hg for mercury. Silver, Ag for silver. Gold, Au for gold. And platinum, Pt for platinum. So the song says, Kwame Nkrumah can marry all common Zambia females simply provided he could have silver, gold, and platinum. Kwame Nkrumah can marry all common Zambia females simply provided he could have gold, silver, and platinum. And carbon and hydrogen that are part of the series are actually not metals, but they are there for a reason. For instance, it has implications for what we call the extraction of the metals from its ore. All metals that are above carbon, meaning they are more reactive than carbon, can only be gotten from their ore by electrolysis. You cannot get metals that are above carbon from their ore by reduction with carbon, or reduction by carbon or carbon monoxide. Why? Because they are more reactive than carbon. So we get them through a process we call electrolysis. So you see aluminum is the immediate one above carbon. Aluminum is gotten through a process we call electrolysis, not by reduction by carbon, and so on and so forth. So one of the properties of acid is that any acid that is above copper, any metal that is above copper, do you see where, okay, where copper is? Copper is just below hydrogen. Copper is just below hydrogen. In some books, you see hydrogen is used as the basis. It's the same thing, because hydrogen is actually not a metal. So you can also say that all the metals that are above hydrogen in the reactivity series, anytime they react with an acid, they displace hydrogen and they give off hydrogen gas. You see, this reaction over here is a displacement reaction. Magnesium is above hydrogen, so magnesium can displace hydrogen. That's one of the properties of acids. Acids react with metals to liberate hydrogen gas, but not all metals. It is only metals that are above hydrogen in the reactivity series. But my people, wait. The first element over there is potassium. Okay. Reactivity actually decreases as you go down this series. So potassium is the most reactive element over there. Then you have sodium. Now, you know potassium and sodium are in the same group of the periodic table. And sodium comes before potassium. Okay? Sodium is above potassium in that series. Now, if I'm telling you that potassium is more reactive than sodium, what does it mean to you? Does that not tell you that reactivity increases down the group? You are very analytical, deductive. You agree with me. That what I'm telling you is that reactivity of the metals increases down the group in the periodic table. That's the only way by which potassium can be more reactive than sodium, because potassium is at the bottom of sodium. What does it tell you? It tells you that elements like francium, cesium, francium, rubidium, that are not in this series are even more reactive than potassium. You're following? So even though they are not in this series, doesn't mean they are not reactive. This series only serves as a basis for you to be able to deduce others. If I ask you potassium and francium, which element is more reactive? Of course, it is francium. Francium is more reactive than potassium, exceedingly reactive than potassium. The fact that it is not in the series here doesn't mean it's not reactive. Now, what does that also tell you? It tells you that reactivity decreases across the period from left to right. So you take elements that are in the same period, like sodium. After sodium, you have, magnesium in the same period. After magnesium, then you have aluminum. Of course, you can see aluminum is below magnesium. Magnesium is also below sodium. It follows very well in that order. But you should be able to make deductions. That's the point I'm making. So that if I give you an element that is not in this series, okay, but you can make the deductions, because all elements will certainly belong to the periodic table. Okay, I give you an element like beryllium. You should know where to put it. Beryllium is in the same period as lithium. Will beryllium be more reactive than lithium, or will be less reactive than lithium? It will be less reactive than lithium, because reactivity decreases across the period. It increases down the group. It increases down the group because metallic character increases down the group. That is the reason why reactivity increases down the group. For the metallic series, for metals, metallic character increases down the group, but metallic character decreases across the period. That's why you have metals to the left and non-metals to the right. As you move from metals to non-metals, metallic character decreases, metallic behavior decreases. But metallic bond strengths, metallic bond strengths increases across the period, not decrease. Metallic bond strength, the strength of the metallic bond that is formed between the atoms, the positive lattice and then the delocalized electrons within the metal, within the element, it decreases, it increases across the period. That's the strength of the metal. That's why aluminum is more metallic. Aluminum is more metallic. Aluminum is more metallic than an element like sodium that belongs in the same period. It's more metallic. Metallic bond strength is determined by the number of valence electrons and the size of the atom. The higher the number of valence electrons and the smaller the size of the atom, the stronger the metallic bond between the atoms of the element. Okay, let's come back. One of the chemical properties of acid is that when they react with metals, hydrogen gas is liberated. That's the point I'm making. You need to remember this. Very, 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 very important. Anytime acids react with metals, hydrogen gas is liberated, but not all metals. It is only metals that are above hydrogen in the reactivity series that end up liberating hydrogen gas from acids. For metals that are below, nothing happens, no reaction takes place. So if in place of magnesium, if it were copper, copper is below hydrogen, copper cannot displace hydrogen. The product you write will be no reaction, nothing will happen in that case. Okay, so the first one with metals, what I mean by that is acids react with metals. And what happens when they react with metals is what I've just told you. Then acids also react with bases. And bases are metal oxides and hydroxides. Okay? If you are not defining bases according to BrØnsted-Lowry, Lewis, Arrhenius, a base is simply the oxide of a metal or the hydroxide of a metal is a base. We define bases as oxides and hydroxides of a metal. Acids are capable of reacting with bases, whether it's an oxide of a metal or it's a hydroxide of a metal. The base dissolves in the acid and neutralizes it. A salt is formed. Okay, what people call the neutralization reaction. Neutralization reaction, by that's what we are told in GHS in chemistry. I will be telling you emphatically that not all acid and base reactions are neutralization reactions. Not all. We'll look at that. We'll see why it is so. Some acids and base reactions react, and then the resulting solution is acidic. Some acids and bases react, and then the resulting solution is basic. If you have more acid than base, the resulting solution will be acidic. You can't say it's neutralization. Because if you test the pH of that solution, it will be in the acidic region. If the base is more in terms of moles than the acid, the resulting solution will be basic. It is only when you have equimolar, concentration, equal moles of acids and bases reacting, that you get a resulting solution neutral. And when you test the pH of that solution, it will be 7, exactly 7. They are the only solutions whose reaction we can describe as neutralization reactions. But just know that acids react with bases to form salt and water, a process we call neutralization process, that's all. Then acids also react with metal carbonates or metal bicarbonates. And anytime an acid reacts with a carbonate, when I say carbonate, I mean a compound with CO3, that's carbonate. It could be the carbonate ion itself, or it could be the bicarbonate ion, the HCO3. Carbon dioxide gas is always liberated. So I said with metal carbonates, effervescence occurs, salt, water, and carbon dioxide gas is produced. Effervescence is the evolution of a gas. Any question? These are the three main properties of acids. If anybody has any one you can think of, let me know. Reaction with metals. They liberate hydrogen gas when they react with metals. And don't forget the metal has to be above hydrogen in the reactivity series before that reaction can happen. Then reaction with bases. Anytime they react with bases, they form salt and water only. The process we call neutralization reaction generally. Then reaction with metal carbonates. Anytime they react with metal carbonates, carbon dioxide gas is always evolved. There is effervescence. Effervescence is bubbling of gases, evolution of gases is what we call effervescence. Okay, so you see normally in the lab, what you see is bubbles. When you open a bottle of mineral, okay, you see what happens at the top. As if it is it wants to boil. Okay, that is because these drinks are carbonated. There's carbon dioxide in them. That's what it means. So the carbon dioxide has been trapped inside the bottle for a very long time. So when you open the lid, the bottle, what you see is the carbon dioxide trying to come. All the gas would like to come out at once. Boom. Okay. So that's what you see. That's the bubbles you see as if they are boiling. You see at the top of the drink. That's what we call effervescence. It is an indication of the presence of a gas wanting to escape into the atmosphere. And I'm saying that anytime acids react with carbonates, you see like the reaction you see here, HCl reacting with calcium carbonate. Look at the products, carbon dioxide is formed. And so there will be effervescence. The gas would like to escape. As for gases, when they are produced, they wouldn't like to stay in the container. They like to escape. And the process of trying to escape is what produces the effervescence, that fluffy, appearance you see on the surface of the solution. I'll pause here. If anybody has any question, let the person ask. Otherwise, I'll bring the class to an end. When we meet again, we'll look at chemical properties of bases. And then we'll look at sources of acids and bases. Where can we get acids and bases from? And then we'll begin salts. The topic is acid, base, and salt. Then we'll look at salt. What salts are the types of salt we have, where we can get salt from, and so on and so forth. And that will be the last aspect of the non-calculation aspect of the acid, base, and salt before we delve into the calculation aspect.